In this final section, we'll be looking at another very different type of non renewable energy, which is nuclear energy. And a helpful way to understand nuclear energy is to contextualize it in relation to chemical energy, which we have talked about several times in this class. Chemical energy is a type of stored potential energy that is contained within the bonds between atoms of a molecule. That energy is released and can be captured when the bonds are broken, of course. Nuclear energy is another type of energy that operates on an atomic level, but it's not stored in the bonds between atoms, but rather in the forces that hold the protons and neutrons together inside of an atom's nucleus. Remember that protons are positively charged, and because they all have the same charge within an atom's nucleus, they repel each other. They want to get away from each other, but there is this force called the strong nuclear force that holds them together within the nucleus. And the strong nuclear force stores an incredible amount of energy. And just like with chemical energy, that energy is released and can be captured when the nucleus of the atom is split apart, which is a phenomenon called nuclear fission. There are several ways to induce nuclear fission. In the most common method, a neutron is fired at a uranium atom, specifically the isotope uranium 235, which causes it to split. What is uranium and why is it used? We'll address that in just a moment. But the effect of this is that the nucleus of the uranium atom breaks down, and in the process, some of its neutrons are scattered. Those neutrons then go on to bombard other uranium atom in the vicinity, which causes them to split apart and more neutrons to be scattered. So there's this chain reaction of nuclear fission leading to more nuclear fission. And each time an atom's nucleus breaks apart, heat and radiation energy are released. And nuclear power plants will gather that energy and convert it to electricity, as we will see in just a few slides from now. But let's get back to the question of why uranium. What is it and why is it used for generating nuclear energy? Uranium is a naturally occurring radioactive element that is found in the Earth's crust. It has three isotopes. And remember, isotopes are variants of an element that have different masses because they have different numbers of neutrons. So there's uranium 238, meaning a mass of 238, uranium 235, and uranium 234. The isotope of choice is uranium 235 because it has several advantages. It emits high levels of heat and radiation when the nucleus is split, and that energy is ultimately what we're after. And it also emits lots of free neutrons from its nucleus when split. So the scattering effect and the chain reaction is very strong with uranium 235. Uranium is found in rocks all over the world, but is relative but in relatively small amounts. So gathering significant amounts of it to power nuclear reactors can be quite a process. And the amount of uranium found on Earth is finite. There's a limit to it. It's not infinite. Therefore, it's considered a non-renewable energy source because it has the potential to run out. So, how is uranium obtained for the purposes of nuclear power generation? Well, the first step is mining it. Uranium can be mined through conventional approaches, which include surface mining and underground mining. We talked about these when we were looking at coal earlier in this chapter. There are also unconventional approaches to extracting uranium. One of these is called solution mining, which is where boreholes are drilled into a uranium deposit, pipes are installed in the holes, and then chemicals are injected down into the deposit, which will dissolve the solid mineral uranium, and then it's pumped back out as part of the chemical solution. In that lower photo, you can see one above ground component of a solution mine. So as you can imagine, these have less of a footprint in terms of ecosystem destruction on the surface. And then there's another interesting approach that isn't really well developed enough to work out at a production scale yet, but seawater recovery of uranium is also being researched And this is where special materials are used to filter uranium out of seawater because there's a very low concentration of uranium in seawater, about 3 to 4 parts per billion. Not enough to be harmful, but if you can collect and concentrate enough of it in a passive filter system, it could serve as a fuel source. However, as I said, that's not really viable yet. It's still being developed. Conventional mining is still by far the most common way of extracting uranium. And conventional mining yields uranium ore, which is rocks where uranium is only one component of the structure. You can see an example of a chunk of uranium ore in the upper picture. So the ore has to be refined through milling. Milling crushes and grinds the ore into a fine powder, and then the chemicals are applied that separate the pure uranium from the other components of the rock. The non uranium waste produced from this process is called mill tailings, while the purified uranium power is called yellow cake. And that's what you see pictured in the photo on the bottom. The next steps are called conversion and enrichment. And these steps are dedicated to taking the pure uranium and further separating it out to get the higher concentration of the most desirable isotope. Because remember that there are three naturally occurring isotopes of uranium 238, 235, and uranium 234. Uranium 235 is the isotope that has those desirable qualities. And so you want to get as much of that particular isotope as possible. And the way of concentrating that uranium 235 is by converting first the yellow cake into a gas in a process called conversion. This is done by adding hydrofluoric acid and fluoride gas to the yellow cake, which results in a chemical reaction that converts it into uranium hexafluoride gas or UF6. And once it's in gas form, enrichment can take place. And during enrichment, the three isotopes are separated so that you just get the UF6 molecules containing uranium 235. And then finally, the enrichment uranium 235 is sealed in canisters and cooled until solid before transporting to the fuel fabrication facility. The final fuel fabrication step prepares the enriched uranium so that it's ready for use in the nuclear power plant. The enriched UF6 is made to undergo a chemical reaction that transfers it into uranium dioxide powder, which is then compressed and molded into small ceramic fuel pellets, which you can see one such fuel pellet pictured in A. So quite small. But a single pellet yields roughly the same amount of energy as 150 gallons of oil. The pellets are stacked and sealed into tubes called fuel rods, which are then bundled together to form a fuel assembly, which is what you see pictured in C. And this fuel assembly is what gets placed in the nuclear reactor at the plant. There are multiple different ways that nuclear power plants operate, but the most common type is called a pressurized water reactor. In a pressurized water reactor, the fuel assembly is placed in a reactor and fission of the uranium is initiated. And then energy from the fission process is used to heat a stream of pressurized water. The heated pressurized water passes from the reactor into a steam generator, which transfers the heat to a separate stream of water, which boils and vaporizes. And the reason why this is done is because the water that is heated directly by the reactor is exposed to radiation, so it has to be kept separate and compartmentalized away from the rest of the power plant. The steam that is produced in the steam generator flows to a turbine and forces the turbine to spin, and the turbine is connected to a generator, so the spinning action is used to produce electricity, which is then sent out onto the grid. And then the steam that spun this turbine gets recycled. It's condensed back into liquid water by a stream of cool water from a surface water source, like a river, similar to a coal fired power plant. And then the liquid water is returned to the steam generator to be vaporized again, while the cooling water is returned back to the surface water source. So that's how a nuclear power plant generates energy The last thing we need to talk about in this section is the benefits and drawbacks of nuclear energy. One major benefit is the fact that, unlike combustion, nuclear fission does not generate the criteria pollutants that are associated with fossil fuels, such as sulfur dioxide, carbon monoxide, nitrogen oxides, and ozone. Nuclear fission also does not emit carbon dioxide and therefore doesn't contribute to the enhancement of the greenhouse effect in the same way. Furthermore, uranium is significantly more energy dense than fossil fuels. This table here gives you a sense of how much more energy can be obtained from uranium fission than from combustion of various other fuel types. Combustion of 1 kilogram, about 2 pounds of wood, generates 16 megajoules of energy. Combustion of coal, 24 megajoules. Crude oil, 44. Gasoline, 46. Natural gas, 55. Uranium, 3,900,000. Per unit weight, there is simply no comparison between the amount of energy you can get out of uranium that is mined versus fossil fuels. This means that production of energy from nuclear fission requires less mining and therefore less ecosystem damage because you get more energy for less material. A final benefit is that nuclear energy represents a clean energy supply that does not vary with the seasons. Other types of clean energy, like wind and solar, can vary significantly over the course of the year. Some parts of the year have more sun, some have less sun, sometimes are windy, sometimes are less windy. Um, Geographically, we're limited as well. We might not get a lot of sun in Northern Europe. Nuclear energy is not tied to those seasonal variations or geographical variations. Even in Arizona, which is a hotspot for solar energy for obvious reasons, we get 10% of our energy from solar, but almost three times that, 29% from nuclear. And that's thanks to the Palo Verde nuclear generating station. Palo Verde, which is located near Tonopah, west of the Phoenix area, is the largest nuclear power plant in the country. It produces 32 million megawatt hours of energy every year. To give you perspective on how much that is, the largest solar farm in the country, which is Topaz Solar Farm in California, covers 4,700 acres and produces only 1.3 million megawatt hours per year. The Palo Verde plant, including all of its reactors and all of its water reservoirs, covers 4,000 acres. So less land for way more energy. Of course, there are also drawbacks to nuclear energy. A big one is disposal of radioactive waste material. Waste material is classified as either low level radioactive waste, which is of the least concern, or high level radioactive waste, which is of the most concern. One major source of low level radioactive waste is mill tailings, which is the waste rock material that is separated out during the refining of the uranium ore. These are dealt with by burying them under a layer of material like clay to prevent radon gas from escaping. This photo shows a site where mill tailings have been buried outside of Moab, Utah. Other low level radioactive wastes include any tools, cleaning materials, or protective clothing worn by workers that come into contact with sources of radiation in the power plant. And there are special regulations for how to deal with these contaminated materials as well. The high level radioactive waste is what is used for fuel assemblies. When a fuel assembly is spent, meaning its energy generating potential has been fully run down, it will be first stored in a specially made water pool that will both cool the fuel assembly and also prevent radiation from escaping. And after that, the spent fuel assemblies may be removed to a dry storage facility, such as the one that you see in this photo, which is made of special radiation blocking materials and relies on airflow for cooling. Lastly, the most rare drawback, but probably the one on everyone's mind when they think of the hazards of nuclear energy, is nuclear meltdown. Nuclear meltdowns can potentially cause widespread radioactive contamination of air and water in the vicinity of the plant. The most well known and most devastating meltdown was the Chernobyl disaster in 1986, which took place in what is now Ukraine, but was at the time the Soviet Union. The meltdown of the power plant at Chernobyl killed 31 workers, sickened or caused cancer in thousands, and contaminated the region with radiation so that there is now a so called exclusion zone around the power plant that is not safely habitable. Other notable accidents include the Fukushima disaster, which occurred in Japan in 2011 when an earthquake and resulting tsunami destabilized the nuclear power plant. However, there were no deaths directly from this disaster. Some people died during the ensuing evacuation, and various sources predict that eventually there will be several hundred cases of cancer that develop in the population that was exposed. The nuclear accident that's closest to home for us was the Three Mile Island partial meltdown, which happened in 1979 in Pennsylvania. This was not a full meltdown, and so a worse disaster was averted, and follow up studies have concluded that there were no measurable long term health effects resulting from it. So, as you can see, nuclear energy has its risks. Those are the major nuclear meltdowns we just covered here. But there's also no other clear energy source that comes close to its productivity. In the next chapter, we'll be taking a look at some of those other clean energy sources, ones that are considered renewable.